It's early evening, and you sat upon a crudely made boat, floating along the Nile River. Suddenly, you hear gunshots, an explosion in the distance. A man with an amazingly dashing shock of blonde hair appears in the distance and is soon running along the opposite bank. He beckons you. Catch! It's Michael Douglas. And he sends something wrapped in a cloth over the water. You catch the package, and you open the cloth wrapping, and inside you find a jewel. You can feel its power washing over you. Now fly, you fool! You pull the oars. Adrenaline takes over, and soon you are far, far away. Oh my goodness. But the heat of the sun, the tiredness in your arms, you pass out and you dream. And in your dream, you're in a church. It's always a church. Inside the church, everyone has gathered and they're waiting to see Brian Shirai.
Thank you. So, we live in an amazing time. Recently, Pluto has been in the news. Humans have sent a robotic spaceship billions of miles to fly within a few thousand miles of the planet, taking pictures and basically more than about 50 gigabytes of data, and start sending it back to Earth. The scientists are saying that the surface of Pluto might be more recent than the amount of time that bees have existed on the Earth. We've also sent people to the moon. And we did that with less computing power than any of us who have a smartphone have in our pocket. So, about 100 years between manned flight and the Wright brothers and actually sending a spaceship to Pluto, putting people on the moon. So all of us with a smartphone have more computing power in our pocket than existed in the entire solar system 100 years ago. Which means that we have hundreds of millions of times more computing power than existed about 100 years ago. This is a picture of 1 byte of RAM from the ENIAC computer. Technology has been pretty amazing. This is a graph of GDP and our energy usage. You can see that we're getting much more efficient. But not everything is going that well. We're not hundreds of millions of times happier or wealthier, healthier. The idea that income in the United States, one of the richest countries in the world, can be going down is a problem. It's a big problem. So what do we do about that? My answer is that what we need is we need to foster a Cambrian explosion of work and interest in programming language. So the Cambrian explosion was a time in Earth's history where most of the diversity that we see today, and actually much more, because a lot of it died out, originated. So in this talk, we're going to look at the alternatives, what we'd actually do with all of our effort in working with computer systems today, this amazing amount of compute power that we have. And we're going to look at what I'm arguing for, which is programming languages, and two very specific things about that. One, how to foster programming language development. So that's the what. And then the who is who's going to be doing the programming language development. So where we spend most of our time today, we spend it in these different areas. One of them is architecture. So service-oriented architectures, microservices. We spend a lot of time looking at how we put together components that we use with our computers. One of the challenges with architecture is that it can be such a critical piece of the application that you don't get to evolve it much. You know, it's like you can do a renovation, but you imagine a structure like this church, you're not going to change something really basic about it without really altering the entire structure. So architecture, changes to architecture impose a rather high cost. We also have infrastructure. I'm using the word in a sort of narrow sense here, right? But when we look at stuff like Docker or cloud, how we organize, how systems talk to each other, again, we're learning things and we're advancing in that area, but it's something that requires a great deal of change, right? So hybrid cloud, for instance, this idea that you can have some stuff in your data center and some stuff out there allows you to reuse some stuff, but it still imposes a big cost, and it's a fundamental sort of piece of what we build. We also spend a lot of work in what I'm calling platforms. So if you make a native app, your native app probably only works on iOS. We have tools where we can try to make an app that works on iOS and Android, but most people that work with those, they end up writing a native app for one or the other. .NET is another one. So to move forward, right, there's, again, a big cost. We can't easily just evolve a system that we've built for iOS and start leveraging it on Android. And then there are frameworks. If we work with computers, probably this is where we spend most of our time. So if you're doing something in Rails and then Ember comes out, these can kind of work together because they stay on opposite sides of the room. But if something was really great in Django, you can't start using that in your Rails app, right? You have to recreate all that effort in Rails, or you give up your Rails app and you move over to Django. And then there's one of my favorites, the development methodology. So Agile is still very popular. Lean is becoming more popular. One of the things that I think about when I think about a development methodology is that people are willing to do almost anything to avoid shipping working code. So we will spend a lot of time about, how are we going to have our meeting and how are we going to estimate. We're going to assign these points, all these sort of things. When actually we have the ability, something like Rails New, I can create a new Rails app and have it in production in 10 minutes. But it's been my experience that we'll wait weeks, if not months, before we actually try to put it in production. And a lot of the stuff that we do in between, falls under this development methodology. And then finally, there's the general purpose programming languages that we use. So if you program a computer and you're not using something like ASM or something similar to it, you're probably using a general purpose programming language, a programming language that was built to try to solve a big class of problems. And in doing so, there is a bunch of trade-offs that were made, right? So you can't have your marbles, in a sense, all on one side of the box, right? When you think of something like the trade-off between memory and CPU usage, if you build into your language something that uses a lot of memory and someone else wants more efficient CPU usage, you can lessen your CPU usage by using more memory, but if you're memory constrained and you have a fast CPU, you want to move it the other direction. So general purpose programming languages have to make that trade-off in a way that's going to satisfy a lot of people. So underneath all of these things that we spend most of our time working on, there's actually programming languages, right? Programming languages are fundamental. When you think of something like an operating system, you know, Unix, the prevalence of Unix and the utility of Unix has meant that C as a programming language, which is not a particularly great language, is so deeply embedded in everything that we do that it's very hard to kick it out, right? The same case can be made for JavaScript on the web. Programming languages, so why I want to focus on programming languages is because they underlie all those other areas that we talked about. But in order to understand the real utility of programming languages, I want to step back for a second and think about the question of why do we have hundreds of millions of times more computer power today than we used to? And that idea is this idea of cost gravity. The term cost gravity I learned in a book by Peter Hitchens, the Zero MQ author. The book is entitled Culture and Empire. But we're familiar with the idea. If we've heard of Moore's law, the idea that the number of transistors on a chip doubles about every 18 months, it's the same idea. It's an example of cost gravity. And what it essentially means is that over time, the cost of something goes down by an exponential graph. And the reason for that is because living things process and share information. So that's the reason that this exists. It's not a magic thing. It's not, if we sit around, it's not going to happen, right? It happens because we process information and because we share information. And all living things do this. The interesting thing to me is that there are three very interesting inflection points on this graph where what is possible changes. The first of them is where something is just too costly to even be built, right? So 100 years ago, we didn't have computers. It's not just that the material costs were too high. The actual costs in human beings doing the research necessary to create something like a computer was enormous, right? At some point, the cost goes from impossible to possible, and we get something custom, right? So IBM or some company like that, the ENIAC is a good example. We built a custom computer. It may have been generally useful, like the ENIAC to do math, but it was a single sort of instance of that. As the costs continue to drop, we get into this area called what I call general purpose. Somewhere in the 80s-ish, the costs of personal computers dropped enough that an average middle-class family in the US could buy a computer. What I think is that a lot of times we think that general purpose is sort of the end point. We get to something very general purpose, you can use it everywhere, and that's sort of where things go. But I think there's another step beyond that that's specialized. And when you get into specialized, the cost drops even further, and you take some aspects of the general purpose solution, and you switch the compromises that you're making, and you get to take advantage of that reduced cost. So with our smartphones today, they're not just general purpose computers, but they're an assembly of custom parts. So the accelerometer and the GPU and the CPU and the flash memory controller, all those things are little computers that have been specialized. Another interesting thing to me about this idea of cost gravity is that we're often confronted with systems where over time the complexity grows, or basically it can be the complexity or the cost to maintain it, and at some point you get to where this big rewrite occurs or the system is replaced. And why this is interesting is that when you get to the point where you're about to replace it, there's a lot of oh my God, what were we thinking? Why did we do it this way? And I don't think that it's because we were making really bad choices before. A bunch of people didn't just sit down and say, oh, I could clearly make it the right way, or I could do it this terrible way that will require a rewrite. But instead, you tend to make it wherever you are on the cost curve, and then as the cost curve starts to drop and you're not tracking it, you get out from that, and then at some point you're like, this distance between our cost and the cost curve is so great that someone rewrites it. But when we rewrite it, in my experience, we tend to repeat the same behavior. We drop down on the curve, and then we make a new project whose cost is going to go out over time. And what I think that we need to do is build in the mechanisms that would allow us to track the cost curve as it reduces. So one of my goals is this idea of being able to use the investment that we've made, but reduce costs by doing low-cost experiments over time without having to replace the entire existing system. And as a sort of quick example of this, this cost curve in action, these are costs for different things in the US, right? So we can see that housing, personal care, down to toys, personal computers, television, way down. The super interesting thing to me on the flip side is, why are costs going up? Why in the world are we at like college tuition going through the roof? So this to me is an opportunity to take advantage of the smalling costs. Somehow the way the system is made up is not actually allowing that to happen, right? So there's an opportunity there. And again, the reason that I think that languages are important is because they are our best tool, the best tool that we've been able to figure out for processing information. Fundamentally, what we do with our programming languages is we process information. So that's why I'm focusing on languages. Now, we have a little bit of a problem. Recently, Business Insider ran a story titled "The 12 Most Influential Programmers Right Now," or living, or something. Anybody notice a problem with this? They're basically all white men. So there's two aspects of why that's a problem. There's the idea of sort of fundamental equality, right? I think that in large measure, part of the reason that this is the case today is because the privilege and opportunity that comes from being a white man in the world means that the effort that they had to put into basically getting to the point on the cost curve was much less, right? So they were able to work on a computer at home because they actually had time and a computer at home, or access to a computer at a university or something like that. So that's one aspect of it. Improving fundamental equality. But there's another aspect that I don't hear talked about that much and is very important to me. And again, from the perspective of equality, I think it's bad and it sucks that there are all white guys here. There are no people of color, and there are especially no women of color. The reason that that's bad, besides the equality reason, is because diversity of viewpoint is important, but diversity of problems is even more important. Fundamentally, all the progress we make is solving problems, right? So I don't go into the field and try to hunt down an animal. I go to the refrigerator and get food out. I don't have to travel for days to talk to somebody. I can call them on the phone. We're not really creating anything new. All the things that we're creating with technology are simply solving problems that we all have. And creative solutions to those problems means that we need a diversity of problems to solve. So we're going to talk about two things. I want to talk about who is going to be working on these programming languages, at least who I would like to encourage to work on it, and how to foster that, and then what. Some things that I think can really help us take advantage of the falling cost and work on programming languages that can make us much more efficient at using this amazing power that we have at our disposal. So, who? One of the challenges of working in open source is that the sort of entire ecosystem is fairly ad hoc. people solve a problem, they kind of get together, and it's almost like planning itself is a bad idea, right? Businesses do planning and forecasting, and so in open source, we just get together and solve some problems. But from my experience for years working on Rubinius and interacting with other open source projects, one of the most important things to me right now is actually defining roles for things that need to be done. And most of those roles aren't technical. There's a big bias in a lot of projects that your top coders are your sort of core team or something like that. Really, coding is what matters. But in fact, to be effective, we need far more roles than just people who are writing code. And so one of the goals that I have for Rubinius is to very clearly define some of these roles and look at things specifically like, and this is not a sort of made-up title, but really someone who is somebody who's actually looking at diversity and how we can specifically increase diversity. So the laying out of roles and not just saying like, oh, we'll tag a few tickets on our bug tracker as tickets that new people could maybe tackle, but really saying like, what are all the things that we need to be successful? And then combined with that is this idea of how we make decisions. So most of the organizations that we will be a part of and interact with are based on this hierarchical structure. And the key component of this structure is that your authority to make decisions derives from where you exist in that structure. If you're at the bottom, you get to make very few decisions, and if you're at the top, you get to make a lot more decisions. Switching from that hierarchy to this hub and spoke or sort of wheel architecture is not fundamentally changing anything. So many open source projects have this sort of structure. There's one or a few people at the very center, and it might look very level, but it's really decision-making is concentrated in the middle, and everybody else is just sort of pushing things up. So neither of those, I think, take advantage of the actual potential that people can bring to solve problems. So there's a very interesting book called Reinventing Organizations that focuses on a different way of organizing. And I like to imagine it more like a network, where some of the positions in the network may have a role to play that's more integrative, but you don't have decision-making deriving from where you are, your position in the structure, but sort of what you're doing. So the connections become more important. I don't know who actually said this, but I read somewhere where the idea is that when you go to a network or a service architecture model, it's the things that happen in between that become more important. So it's not the individuals, it's how you're collaborating. Along with this new structure is this idea called the advice process. So how do we make decisions? One of the things that is becoming more popular, Rust, Ember, are doing this idea of CFP, or is it, no, CFP, oh man, the internet thing, RFC, there we go, many acronyms. Okay, so the reason I have a problem with that is that you tend to replicate that hierarchical structure where your authority to make decisions means, basically, you can take input, but it's going to work its way up to this small group of people who are going to say, okay, this is what we're going to do. This is the feature that we're going to add, or this is how we're going to make the thing work. The advice process contrasts with that by offering a structure where you make decisions according to the following things. First, anybody is empowered to make a decision. It just requires that you follow this process. And the process is essentially, you see a problem that you think needs to be resolved. You can describe your solution to the problem. And this is key. You have to seek input from the people who would be affected by it. You don't get to just sit there and say, well, I'm the decision maker, I think this is what we'll do. You have to seek input, and you have to respect the input of the people who would be affected by your decision. And then you need to consult people with relevant expertise. And what I think is so interesting about this is that different people have different expertise all the time. If you base decision-making around your position in a hierarchy, then when someone has a great idea or deep life experience about something, they only get to contribute to that if the person in that position bothers to consult with them and then takes them seriously, right? So in the advice process, you have to seek advice from people with relevant expertise. And if someone's gonna say, hey, I really recommend that you do it this way, and you say, no, I'm gonna do it this other way, you should be able to articulate that. So that's the who. Specific roles, focusing on diversity, focusing on how to involve the greatest number of people, and then offering a process that they can make decisions, solve problems, without resorting to this position in a hierarchy. So now the what. Now, oftentimes people say, don't be negative, but I'm going to focus on 4 things that I really do not want and I want to avoid in building support for experimenting and working with specialized languages. So the first thing that I do not want is I do not want to be forced to choose between static typing and dynamic typing unnecessarily. If you work in a programming language, I would bet 99.9999% sure that you work in a language that either is statically typed or dynamically typed. And then we build up big walls and process around whether it's a good idea to be statically typed or dynamically typed. I think there's a lot of cost to it, and I do not want to be forced to make that decision unnecessarily. I also don't want to be told that I can use only a single type system. I like type systems. There's an awful lot of them, and almost every language that we use today decides that there will be one type system and then forces you to use that one. I don't want to be forced to decide between compiling my code now and being able to run my code on a virtual machine or some sort of instrumentation that gives me a much better view of what's happening. So again, this is something, if you're going to use Go, it's going to be precompiled. If you're going to use Python, it's going to run on a virtual machine, sort of thing. And then finally, I don't want to choose a particular programming paradigm. I don't want everything to be an object, or I don't want to be told, like Rich Hickey likes to say, that there's object malarkey and you should be using functions. So those are things that I do not want because I think they have really bad effects on our ability to experiment. Right? So the goal is to experiment at the lowest cost, right? So what I do want, I'm going to focus on instruction set because in my experience building a virtual machine, it's sort of taken for granted that a computer or a virtual machine will have an instruction set, but I think we've tended to make a lot of assumptions that really box us in. And the more I worked on it, the more I realized that there were really 5 different things that I was trying to achieve in making a platform to run a programming language, and I needed all of them. So we're going to talk about stack instructions, register instructions, parsing instructions, assertion instructions, and instrumentation instructions. So real quick dive into virtual machines. A lot of virtual machines, the JVM, for instance, Rubinius as well, it's a stack-based virtual machine. Now, we often hear things like, oh, Lua has a register machine, and that's why it's so fast. It's not. There's no difference between a stack machine and a register machine, fundamentally. They do exactly the same thing. There are reasons to use a stack machine. It's super easy. If you've ever used RPN calculator, that's a stack machine. PostScript, stack language. They're very easy to emit code. You can compile code and quite easily generate stack-based instructions. They become very difficult to do analysis for, though, because of the position, what's actually in a stack location can change. And so the analysis code around it becomes very unwieldy quickly. Register instructions are quite natural as well. They sort of have this almost function call type syntax, right? The cool thing about register instructions is that you can do really good analysis. You can look at the liveness of a register. You can see sort of what is in that register at a particular time relative to these other ones. We need both of these things. And in Remittance, we actually have the ability to have register instructions and stack instructions together. I haven't developed much of the register set yet, but I want these both to be available for people who are experimenting with languages. Since much of language is about syntax, I think that parsing instructions need to be a fundamental part of the machine as well. So a parsing instruction, this is sort of pseudo parsing expression grammar syntax, but parsing instructions are really just a way to describe how we put sort of characters together and what tokens are meaningful. So lexing, splitting up input into specific tokens, and then parsing, or a grammar that describes how you can put those together in well-formed phrases. With something like parsing instructions built in, we can bootstrap a system that's quite complex by using a simpler language, right, at the beginning, instead of having to make that decision about, do I compile this to machine code or do I have a virtual machine? So there's a lot of uses of parsing instructions. The Lua author actually made something called LPEG, which is a machine for parsing expression grammars. It's quite natural to work with this in a machine sort of format, but I don't know of any other virtual machine that actually makes parsing instructions first class. Right? Another class of instructions is assertion instructions. A lot of the stuff we do with code expresses assumptions about the semantics of the program, but they're implicit. So part of the reason that people want static typing is because they say that static typing will help you check the correctness of your program. Well, assertions can help as well, and assertion instructions, by putting assertion instructions in the machine, they can't affect the correctness of the program, but they can basically halt execution if the program is misbehaving. And by allowing them to be, in a sense, a different dimension in your program, you can experiment with adding them or removing them based on your needs at the moment. So instead of editing the code to say, I assert that this value is this, you can actually describe what you want the computation to do and then instrument that with assertion instructions to remove them. And then finally, this class of instructions called instrumentation instructions. And the idea there is that, similar to dtrace, if you've heard of that, it's this idea that you should have something that is impossible to affect semantics, right? So you can't take down production. And it needs to be efficient, right? So instrumentation instructions can coexist with the code, but they can't change the semantics of your program. So you can add them, you can take them out. And then again, from the perspective of, these are all things that I think are really essential to helping foster programming language innovation. There may be some term for this in the literature. I don't know what it is. Okay, almost done. It's called, what I'm using it for, what I'm describing is this idea that we have our languages, which have a particular semantic, and then we tend to describe those in terms of a virtual machine, and then the physical machine below that. And the semantic cone is where you lose semantics from your language and have to recreate them to adequately take advantage of the physical machine. And what I want to be able to do is describe the language faithfully through the virtual machine down to the physical machine. First class support for abstract syntax trees, I think, needs to be in there. This idea of functions and objects actually needs to coexist. Objects allow us to interact between components. Functions allow us to operate on data. I'm going fast because we're running out of time. And then finally, this idea of what, how, and why. I want to know what my program is doing. I want to know how it's doing. And when I get into a bind, I want to be able to figure out why it's doing this thing. So tooling built into the VM to allow us to understand our program along these different dimensions. And finally, this idea of a code DB, which essentially just means that we can associate multiple dimensions of data with our executable code. Now, everybody knows that when we sit down to write our programs, it basically goes like this, right? We start, it's a straight line to finish. We introduce some process to make that more efficient, perhaps. It never goes like this, right? It's more like that. We start and we go around the loop a few times, right? Not even close. In my experience, that's what development looks like. So being able to build on tools that allow us to go into this chaotic place where we're figuring out how to process information is, sort of a core thing that we need to foster programming language development. There's no silver bullet, there's no free lunch. The cost gravity curve doesn't just go down infinitely. The speed of light is real. The physical limitations of what we can actually achieve are real, but in many areas of programming, we don't know what those are. Like, I'm literally not exaggerating. We have hundreds of millions of times more programming power or more computation power than we had 100 years ago. That means we should be able to do hundreds of millions of times more things with it. Fascinating thing for me is that WebAssembly was just recently announced. This means that all these tools to support programming language development can exist anywhere on the web. And that's really exciting. So if you're interested in this stuff, check out our website, rubini.us. The GitHub organization, Rubinius, has a bunch of stuff in it. We have a Gitter chat account. Follow me on Twitter. And finally, I want to say thank you to the company I work for, Innova, for sponsoring me to be here. We are hiring, and we can possibly help out with immigration stuff if anybody wants to come work in Chicago. And thank you to the organizers, So Coded. Fantastic conference, amazing people, speakers, and thanks to all of you.
Thank you, Brian. So we're going into a longer break now, so you have a bit more time.